Hello, ladies and gentlemen, and welcome to Mr. Saucedo's YouTube videos. Today we're going to be talking about the second portion of Chapter 8 in Zumdahl, the 7th edition. That's the chemistry textbook, by the way. And it is all about bonding, and in general, what we've already covered is kind of introductory material about ionic bonds, covalent bonds, and polar covalent bonds. So let's jump to section 8.5. So 8.5 is all about the energy effects that you can find in binary ionic compounds. And so the big question for this is, what are the factors that influence the stability and the structures of solid binary ionic compounds? So when we say that, what are we referring to? So binary meaning two, so we're only looking at like a cation and an anion. Ionic compounds, again, we discussed this in the previous part, so if you need to go back, feel free to go back. The link will be in the description, but the idea is that you don't really have such a thing as a pure ionic bond. Yeah, there is actually a pure covalent bond, but ionic bonds are very unique in the sense that they utilize a transfer of electrons. So an electron or electrons are being transferred from one element to another element, thereby creating ions, right? And the positive and negative charges are kind of what hold them together to make these compounds. But what's the cutoff for when that transfer of electrons happens? And so what we basically said is there is a way of calculating that, but it's all wibbly and wobbly. So no one likes to use that, because then you arbitrarily have a cutoff of, okay, if the difference in electronegativity is greater than this, then it's ionic. And that just isn't the way that it really works. And so we'll talk about that in 8.5 a little bit more in detail. But how strong is that attraction between the cation and the anion? And there is a way of objectively measuring this. And so we utilize a term called lattice energy that lets us know how strongly attracted the ions are to each other in the crystal. Or I guess we could say the lattice, because crystal and lattice are used interchangeably. And so lattice energy is specifically the change in energy that takes place when separated gaseous ions are packed together to form an ionic solid. So when we're going from a gas to a solid, what we're basically picturing here are we have these ions, cations and anions that are far apart and separated from one another. And now we're going to bring them together. And when they go together, they're going to be forming now a solid. So you're basically turning a gas into a solid. And so that's called deposition. It's kind of the opposite of sublimation and stuff. But yeah, so that's kind of the idea. And there is a formula for it. Go figure. Lattice energy is equal to K times Q1 times Q2 divided by R. And so K is a proportionality constant. So who cares what K is? K is not the interesting part of this equation. Q1 and Q2 are really important because they're the charges of the ions. So Q1 generally is the cation. Q2 is generally the anion. And then R is the shortest distance between the centers of the cation and anion. So you can picture it like a measuring tape or a ruler. If you were to put it right at the center of the cation, where the nucleus of the cation is, how far away is the nucleus of the anion? That's kind of what those are. So hopefully this equation looks very similar to another one that we already talked about prior to this. This is almost exactly Coulomb's law. The difference is, well, we have a different constant for Coulomb's law, and R is squared in Coulomb's law. But generally speaking, this is almost the exact same equation, and that's not coincidental. So let's talk about the formation of ionic solids. So there are a lot of different processes and ways that we can calculate the lattice energy. And it doesn't matter which of these processes we use in order to get our gases to solid, because they're all interchangeable. And so that's great. So we've got, a metal that's a solid, and we're turning that into a gas. That's an endothermic process. And just a reminder what that means energy goes into the system. And that makes sense, right? In order to, turn a solid into a gas, you have to apply a certain amount of energy to your metal for that to happen. What about ionizing a metal, right? Now you're going from a gas to an ion, which means that you're adding enough energy to remove an electron from that. And so ionization is also endothermic, requires an absorption of energy. What about dissociating a non-metal? What if instead, we have a non-metal here that is paired up and we want to break that bond apart? Well, again, you're breaking a bond. That means that that's also an endothermic process. Now, what about the opposites, right? So obviously, if you're trying to do the opposite of this, it's going to be exothermic. So what if instead we are forming non-metal ions in a gaseous phase? So in other words, I have my non-metal here. I'm going to add an electron to it, and that's going to make this negatively charged anion. That is an exothermic process. Simply adding an electron is going to release energy as a result of that when we're talking about nonmetals. Now, forming a solid ionic compound, right? So that's taking a gaseous metal and taking a gaseous anion here and putting them together in order to manufacture a solid. So now we're depositing. We're going from gas to solid. That is an extremely exothermic reaction. You're literally taking two things that are gases and making a solid out of them. So that's going to release a huge amount of energy as a result of that. And that energy is the lattice energy. So 8.6, partial ionic character of covalent bonds. So this is where we get into the discussion that we already talked about in the previous part, which is that really no bond can ever reach 100% ionic character, even if we look at compounds that have the furthest electronegativities from one another. And so instead, you can think of that as, again, metal plus non-metal gives you something that we consider ionic. Now, where's the cutoff? Again, it's very arbitrary. And so because the definition of ionic bonding and covalent bonding, right, they're very intertwined with one another. Don't worry too much about, okay, is this 100% ionic? No, it will never be 100% ionic. But take a look at these. We've got, cesium and fluorine here. So we've got cesium fluoride. They're about as far apart as you could possibly get with regard to electronegativity. And notice that it's still, if we're looking at the percent ionic character, it's still around 70%. Lithium fluoride is actually a lot higher when it comes to the ionic character of the bond that's forming between them. But again, that isn't the important part. So don't worry too much about it. Just again, know that a metal and a non-metal, generally speaking, they have very large differences in electronegativity anyway, so they're going to be almost entirely ionic for our purposes, okay? Now, fundamental properties of models here. So keep in mind that now we're going to be modeling some covalent bonds here. A model does not mean it is real, okay? Models are workable, simplified ways of looking at the universe. And so, like it says, models are often overly simplified, and so therefore they can often be quote unquote wrong, okay? But they are a good building block into understanding and creating a workable model of how the universe functions, okay? And yes, models become more complicated and can be modified as they age. And so some of the modeling techniques that we're actually going to be utilizing are pretty old, like a century old, but they still hold up, generally speaking. And so the whole point, though, of utilizing a model in order to understand something in chemistry is that you have to understand the assumptions that are being made so that you don't just think, oh, of course, well, this is the way it always works. This is the way it works under this model, Okay, that's kind of the important part. And again, if a model is wrong, we often learn much more about what's going on than when a model is 100% correct. And I mean, I can just think back to, I don't remember what chapter it was at this point now, but think back to Bohr's model of the atom. It works perfectly for hydrogen, but then it can't be applied to helium, and it can't be applied to lithium, and it can't be applied to any other element on the periodic table. So, or at least not perfectly, right? Unlike the hydrogen model. So let's talk about bond energies, because bond energies make up a huge chunk of what is going to happen on the AP exam anyway. And so utilizing a little bit of what we just talked about, let's break it down. So we just talked about lattice energy. Keep in mind that in order to break a bond, energy must be added to a system. You have to add something like heat in order to break a bond. And that means that it's endothermic. So that means that when we're utilizing energy, like kilojoules or joules or whatever it might be, that the term carries a positive sign. So it's positive kilojoules, positive joules, positive electron volts, things like that. Now, we're doing the opposite, right? Which, again, this little part here is the most misunderstood part, I'd say, of all of chemistry and all of thermochemistry. And a lot of it comes from the fact that biology teachers often utilize the wrong vocabulary when they're talking about photosynthesis and cellular respiration. And because, well, never mind. I also teach biology, by the way. So I make a really big point to talk about this bond energy stuff when we're discussing cellular respiration and photosynthesis, because as a chemistry teacher, when biology students come in with these misconceptions about energy, they often make the same mistakes and then forget about it completely. And then you're like, okay, great, you learned this now. And then, oh, great, you made that same mistake a couple of months later when it was on the midterm or on the final. So in order to form a bond, if you want to form an ionic bond or a covalent bond, energy is released, and that means it is exothermic, and that means the energy term carries a negative sign, like negative joules, negative kilojoules, etc. And so for this top one, for breaking bonds, it normally makes sense. I have something that's bonded together, I have to apply energy or heat to it, and then those bonds break apart. The one that isn't as intuitive is the fact that when you want to form a bond, energy is actually released. So I have all these little pieces. Now, in order to get them, to link together and to form this bond, when they snap together to form that bond, I always picture it like magnets. You're bringing magnets close together, and then eventually they snap together. That sound that you hear, the snapping magnets, that is a release of energy. And it's the same thing with, these little relatively magnetic atoms. When you get them close enough, it's going to lower the potential energy of the system at that point, and that means that there's going to be a net release of energy as a result of that when that bond forms. And so you can think of it like this. I have these reactant molecules. I want to break them into pieces. So when I do that, I apply energy. When I apply energy, they're now all separated. Now that I've separated them, they're going to reassemble into different molecules, and that is going to release energy. Okay? And yes, the difference between the reactants and the products, that is called the change in enthalpy of the reaction. But again, we already talked about that in thermo. So let's talk about how we can calculate these bond energies. So we can calculate bond energy using this equation. So it's the delta H, aka the enthalpy change, is equal to the sum of the number of bonds that are broken minus the sum of the number of bonds that are formed. And so D, like it says here, represents the bond energy per mole of those bonds. They always have a positive sign, and they're always tabulated for you, which is kind of nice. There's always like a nice little table. And so here's a good one here. I have CH3N with a triple bond C, and again, it's a gas. And then it is turning into something that looks almost exactly the same, but notice that the nitrogen and the carbon have now switched spots. So I have a little model here for you of what this reactant looks like and what this product looks like. Here are our bond energies. What is the enthalpy change from this to this? All right, let's work through this, okay? So here is our equation. Delta H equals the sum of Again, the number of bonds that are broken minus the sum of the number of bonds that are formed in order to do this. So that means that I'm going to have this first part are the bonds that are going to be broken, okay? Minus, again, the number of bonds that are being formed. So let's say that I want to break this thing apart into pieces, okay? So the first part I can see here is that I have CH3, this is a carbon, this is a hydrogen, carbon and hydrogen, carbon, hydrogen. So I have 3 carbon-hydrogen bonds. And so a carbon-hydrogen bond is 413. So I have 3 times that number because I have 3 carbon-hydrogen bonds right here, okay? Then I have a carbon-nitrogen bond, okay? Carbon-nitrogen bond is 305 right here, carbon-nitrogen bond. And then I have a nitrogen carbon triple bond. And so that's right here, and that's 891. So I would add all of those together, and that would be if I took this and broke it all into pieces. Now notice that it doesn't matter if the C is on this side or if the N is on this side, it is the same thing. So I could very easily have said a nitrogen-carbon bond instead of a carbon-nitrogen bond, or a hydrogen-carbon bond instead of a carbon-hydrogen bond. It doesn't matter if I flip these around, the bond energy is the same, okay? And so now I want to do the same thing for this. So the first part hasn't really changed. CH3 is still CH3, so I still have 3 times 413 kilojoules per mole. Now the next part is different. I have a carbon-carbon bond now, and a carbon-carbon bond is 347 kilojoules per mole. And then notice that again, I have this little bond right here, which is the exact same thing, just flipped. So 891. Now, when I do my subtraction for the bonds broken versus the bonds formed, I get a change in enthalpy of negative 42 kilojoules. Now, what does that tell me? That tells me that this is an exothermic process, because remember, the negative sign lets me know that, okay, this is an exothermic process that I'm looking at. I'm releasing heat by doing this rearrangement. All right, now, localized electron modeling. So a molecule is composed of atoms that are bound together by sharing pairs of electrons, right? We're talking about covalent bonding now. We've moved on from ionic bonding. That was just the very first section we had to talk about with lattice energy. Now we're only focusing on covalent bonding. And these sharing pairs of electrons are bound to these particular atoms that we are modeling. Now, keep in mind that electron pairs are assumed to be localized, which means that they're located on a particular atom or in the space between 2 atoms. So when we're talking about the space between 2 atoms, we're talking about bonds, like covalent bonds or polar covalent bonds, okay? So we call those bonding pairs of electrons. Those are the ones that are actually doing the bonding. They're sticking the 2 atoms together and lowering the potential energy of the system. Now, lone pairs of electrons are localized on an individual atom. And again, we normally utilize, when we're talking about lone pairs, we use dots to represent lone pairs. For bonding pairs, we normally use lines. So when you see lines, think bonds. When you see dots, think lone pairs of electrons, okay? And so how are we going to utilize this? Well, how are we going to use this? So we're going to use it in a couple of ways. But the first one is we need to first describe the valence electron arrangement of all of the atoms in our compounds. And so we call that the Lewis dot structure or the Lewis structure. And these are the 2-dimensional drawings that you're used to seeing in probably every chemistry class you've ever taken. And then the second part to this is to predict what the actual shape of the molecule will look like in 3-dimensional space, and we use VSEPR theory for that. So VSEPR stands for the valence shell electron pair repulsion model that we're talking about at the end of this chapter. Okay, so to start with, we're going to start with just Lewis structures or Lewis dot structures. So what are Lewis structures? They are a model that show us how valence electrons are arranged among atoms in a molecule. They reflect the idea that the stability of a compound relates to whether or not you can receive or reach a noble gas electron configuration. So here's the way that I've always looked at it. So let's say we have our periodic table and we remove those pesky little transition metals. So The alkali metals plus hydrogen are in the first column. And so generally speaking here, when we're looking at them, they have one valence electron, so a single dot. Then one step over, we have the alkaline earth metals. They have two. Then we have our next column over. Again, if we're skipping the transition metals, we have group 13, and they have three. And then group 14 has four. Group 15 has five. Then we have 6, 7, and then when we reach the noble gases, we have our 8 electrons, except for helium, which only has 2. But helium doesn't really form any compounds, so we don't really care about that. We have neon, argon, krypton, etc. Okay, and so all of the noble gases, when we're talking about them, what we are really getting at is the fact that they have an electron configuration where all of the electron spaces for their orbitals are all filled up. Everything else, so the halogens all the way down to the alkali metals and hydrogen, do not have, a full set of electrons in their orbitals, but they desperately want to have that noble gas configuration. Now, on the AP exam, they don't want you to talk about this in flowery language like I am. They don't want you to say, oh yeah, these elements want electrons. If you're saying that, that's considered too informal. So you would have to talk about stability. So how to make your atom more stable in the compound or in the molecule that you're drawing. So the Duet rule is really just for hydrogen. Hydrogen has a single electron, so to get it to have 8 is going to take a lot of energy and not really going to be realistic. So instead, hydrogen forms stable molecules when it's able to share 2 electrons. So when you hear 2, think duet, like 2 people singing or something. It's a duet. So here is a hydrogen molecule, 2 hydrogens hooked together. And so, a single hydrogen has a single electron, but if you bring 2 of them together, now they have basically shared, their electrons, and now you have 2 electrons. And so the way that we represent that is with a bond. Because remember, bonding pairs of electrons are shared between atoms. And so this is an example of, a bond being shared. These electrons do not belong just to one hydrogen. They belong to both hydrogens. This electron can go around here while this electron goes around here, or vice versa, or they can both go around one and then the other one doesn't have any. It's just because, again, the bond is forming in this situation. Now, what about the octet rule? So octet, oct meaning 8, is for all the other elements on the periodic table. Elements form stable molecules when surrounded by 8 electrons. So here is fluorine. We have 2 fluorine atoms hooked together to form diatomic fluorine. And so this is what that would look like. So remember, according to our little chart, fluorine has 7 electrons. But guess what? If this one has 7 and this one has 7, they can each share an electron, a piece here, and now this becomes a bond. And notice that this one has 2, 4, 6, plus these 2, 8, so an octet. This one has 2, 4, 6, 8. This one also has an octet. So these electrons are free to spend time around this fluorine or to spend time around that fluorine. But either way, you have an octet now. Let's talk about single covalent bonds. So a single covalent bond is when 2 atoms share 1 pair of electrons, and so we represent that as a single line. Double covalent bonds, or double bonds, are when 2 atoms share 2 pairs of electrons. So right here we have a double bond. We use it in carbon dioxide here. You can see that we have 2 bonds represented by 2 lines between this oxygen and this carbon, and then also another one between this carbon and this oxygen. And then a triple covalent bond is, again, when 2 atoms share 3 pairs of electrons. So again, we have 2, 4, 6. So we have 6 electrons being shared here, represented by these lines. All right, so what are our steps for drawing and writing Lewis dot structures? First things first, add all of the valence electrons together so you know how many dots you're supposed to have in your picture. Use a pair of electrons to form a bond between each pair of bound atoms, And then keep in mind that atoms usually want to have a noble gas configuration. The only exception to that is really the Duet rule for hydrogen. So you want to arrange any remaining electrons you have to satisfy the octet rule. Now, when we say that, that means, adding dots to, other atoms, or if you can't add any more dots, forming a double bond or a triple bond when appropriate. Okay, you can't just form it willy-nilly. So the first step is to add all the valence electrons together for your atoms. So let's take the simplest of simple examples with H2O. So we're going to look at water. So if I'm looking at my chart here, hydrogen has 1. I have 2 hydrogens, so that's 2 electrons alone from this. Oxygen has 6, so 6 and 2, that gives me 8 electrons total. Water has 8 valence electrons in its structure. Now, second step, use a pair of electrons to form a bond. So I draw simply a line between my hydrogen and my oxygen, and then this other hydrogen and this, the same oxygen again. So notice that because I have this line here, this represents 2 electrons. So in my picture right now, I have 4 electrons in my picture. Last but not least, only the hydrogens want to have a duet. The remaining atoms, in this case just the oxygen, wants to have octet. So the way I would fix that is by adding dots to my oxygens here. And so now I have 2, 4, 6, 8 electrons, which is exactly the number of valence electrons I was supposed to have. Notice that this oxygen has an octet, 2, 4, 6, 8. Notice the hydrogens each have a duet. They don't have any dots on them. They have just this bond here, and this one has this bond here. So this one is only surrounded by 2. This one is only surrounded by 2. So let's see if we can, kind of complete the octets for the following molecules. So I have phosphorus tribromide here, and then I have hydrogen cyanide. So I already counted the number of valence electrons. If you don't trust me, you're more than welcome to add them up yourself, but this one should have 26, and this one should have 10. So I started at step 2 with just single lines. Now we need to add the remaining dots, or, in some cases, adding a double or a triple bond. So what's the next step? We want to add dots. So the way that we add dots is always to the outer atoms before you add it to the central atom. So when we say outer atoms, we literally mean the ones that are not in the middle. That's all it means. And generally speaking, you're adding them to the outer atoms because the pattern is this. You always try to add electrons to the more electronegative atoms first, because the more electronegative the atoms are, the more likely they are to kind of have electrons around themselves and pull them to themselves anyway. So I'm going to start on this bromine here. So right now I have 2, I have 4, I have 6 electrons, and now I'm going to add 8 and 10 and 12 and 14 and 16 and 18 and 20 and 22 and 24. Okay, I need 26. After you've added them all to the outer atoms, then you can add electrons to the central atom, like that. And so now, notice this bromine has an octet, this bromine has an octet, this bromine has an octet, and the phosphorus also now has an octet. What about for hydrogen cyanide? So same rules apply. And now think about this. I only have 2, I have 4 electrons in my picture. I can't add any electrons to hydrogen because hydrogen just wants a duet. So you will never see dots around a hydrogen. So that means I can only add electrons to my nitrogen here. And so I'm going to do that. And now I have 10 electrons. So you might think to yourself, I must be done. Clearly we're not done because this carbon still only has 4 electrons. So how exactly do I go about fixing that? Well, remember, everything wants to have an octet except for hydrogen. So what I can do is I can share these electrons as a double bond if necessary. So how do we do that? Well, it seems like a kind of a trick, but it's not really a trick. What I can do is I can take a pair of electrons and erase them and then move that as a bond. So I'm going to take the top pair of electrons and erase it and then put that as a double bond. Notice I still have 10 electrons here. 2, 4, 6, 8, 10. Didn't add any extra dots or anything. What did I do though? I moved this so that now it's bonded between the carbon and the nitrogen. So now carbon has 2, 4, 6 electrons. Clearly that's not enough though, so I'm going to erase another pair, and now I have a triple bond. Now look at it. I have 2, 4, 6, 8, 10 still. This nitrogen now has an octet. This carbon has an octet. This hydrogen has a duet. And that's how you draw Lewis dot structures. You add as many dots as you possibly can according to the number you have. And then you have to stop and look and see if everything has an octet or a duet. If it does, like this one, you're done. If it doesn't, then you have to get creative and start making double bonds or triple bonds. So draw a Lewis dot structure for each of the following. Here we go. We have H2. Nice and easy. I need 2 electrons. Perfect. I have a duet. That's all I would need. I can't add any more dots around hydrogen. What about, again, F2? Great. Fluorine's over here. I have 2 of them. That's 7 and 7. That's 14. Great. I have 2, 4, 6, 8, 10, 12, 14. Everything has an octet. I'm done. What about HF? Let's put an H and an F together. So hydrogen's 1, fluorine is 7. I need 8 electrons. So we start with just a single bond. I can't add any dots to my hydrogen because it already has its duet, so I must add dots then to my fluorine, and now I've drawn the Lewis dot structure for hydrogen fluoride or for hydrofluoric acid, depending on how you want to look at it. And that's it. All right, what about NH3? Okay, we started with single bonds here, so let's add them all together. We've got 5 plus 3, that's 8, so I have 6. Where am I going to add my electrons? Well, this already has a duet, this has a duet, and this has a duet. The only empty space is right here, so now my nitrogen has an octet. What about the next one? So again, I have CO2. Again, I have my carbon, I have my oxygen, and there are 2 of them, so when I add that all together, that's 16 valence electrons. I currently have 4. Let's start. So I have 4, so I have now 6, 8, 10, 12, 14, 16. Great. This oxygen has an octet. This oxygen has an octet. This poor carbon doesn't, though. So what can I do? I can't add any more dots, but I can add a double bond, add another double bond. Now my carbon here has an octet around it, and so do my oxygens. Next up, I've got CCl4. So again, carbon's here, it has 4. Chlorine's here, it has 7, and I have 4 of those. So when I add them all together, I'm going to have a cool looking one. So how many electrons is that? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32 electrons. And that is the most of any of the ones I've drawn so far. But when you add them all together, that's how many you should have. You should have 32. Now, what about exceptions to the octet rule? So keep this in mind. There are a couple of general exceptions to the octet rule. The first one is when you don't have enough to make an octet. So the only real exception to that is boron, and it's the only one you'll really ever see. So boron tends to form compounds where it actually has only 6 electrons around itself. So it doesn't complete the octet, unlike most of the other elements on the periodic table. So for example, we have BH3, boron, that has 3. Hydrogen has 1 apiece, but we have 3 of them, so we'd have 6 electrons. So if I were to draw that, it would actually look like this. And you'd think, hey, this boron doesn't have an octet. But guess what? Boron is totally happy just having 6 electrons around itself. So boron is a typical exception to the octet rule. Other exceptions to the octet rule. Now, if you are in the 3rd row or higher, so if we're talking about the periods of the periodic table, then technically things that are in the 3rd row or higher can actually have extra pairs of electrons on their central atom. So for example, SF4, or this is arsenic, so we've got ASBR5. So 34 electrons, 40 electrons, they're really ridiculously big. And so, for example, here, you would fill in your octet, and then you'd still have 2 extra electrons you need to put somewhere. So keep in mind that if your element is in the 3rd row or higher, you can actually put extra dots on the central atom, and that is considered totally and completely okay. It's not ideal, right? But it is an exception to the octet rule. Okay, and same thing here with arsenic. Arsenic here has 10 electrons around it, just like this sulfur also has 10 electrons around itself. So let's try to draw the following molecules utilizing what we just learned about exceptions to the octet rule. So I have like BF3. So I'll just show you, this is what that would look like. Again, we've got boron having only 6 electrons, whereas the fluorines still have to have an octet. PCl5, same exact thing as before also. This phosphorus has 10 electrons around itself, but notice that the chlorines still follow the octet rule here. Generally speaking, when we talk about exceptions to the octet rule, we're only talking about the central atom. That's it. We're not talking about everything. You might think, oh, well, chlorine or bromine or, something like that. If they're on the outside, aren't they also above the third row in the periodic table or in the third row of the periodic table? Yes, they are. But again, the exceptions to the octet rule only apply to central atoms. So if this chlorine were in the center, then yes, that chlorine could definitely have more than 8 electrons around itself. Not ideally, but it could happen. SF6, this one's actually kind of a fun one. Again, this sulfur has 12 electrons around itself. But notice that the fluorines all have an octet. So when there are exceptions to the octet rule, it is only the central atom that we're talking about. We're not talking about, the outer atoms. Those will always follow the octet rule. So let's review real quick. Carbon, nitrogen, oxygen, and fluorine should always be assumed to follow that octet rule. Boron and beryllium often have fewer than 8 electrons. Beryllium is probably never going to show up, but boron is the big exception. Second row elements never exceed the octet rule, but if you're beyond the third row, or if you're heavier than the third row, right, so if you're the fourth or the fifth, you can exceed the octet rule. And don't worry about why. I'll tell you this. When I got my chemistry degree, so when I got my degree in chemistry, I learned why, and it ended up being wrong. So don't worry about why. Scientists used to think they knew why third row elements or beyond third row elements can have exceptions to the octet rule. And they used to tell us what it was. And okay, yeah, this is the reason why. But guess what? That is all really disputed now. And there's no conclusive evidence that what I had learned was actually correct. And again, I'm not ancient, so just keep in mind that it's the way science works. You collect evidence. If that evidence doesn't support your idea or theory, no matter how old it is, it'll get thrown out. All right, now last but not least, when we're writing the Lewis dot structures for molecules, again, you have to follow that octet rule, and you want to make sure that everything except for hydrogen is following that octet rule. And then if you have remaining electrons, you can place them on elements that, again, in the center are above the third period of the periodic table. But again, that's like a last resort. And so what elements are we talking about? Theoretically, it can be any of these, right? But in reality, I'll list the ones that are more likely to show up. Phosphorus, sulfur, chlorine, argon, arsenic. I've yet to see selenium in one of these, but bromine and krypton, antimony, iodine, xenon, and that's pretty much it. Tellurium and selenium, I haven't really seen anything that resembles those, but like I said, the other ones, yes. And if you're wondering about anything below that, no, you're not going to see those. All right, so what about resonance structures? So if there's more than one valid Lewis dot structure that can be written for a particular molecule or ion, then we call those resonance structures. So for example, we have NO3-, so that's the nitrate anion. Let's count how many electrons we're supposed to have. And for some reason, I don't know why, maybe the book does go through it, but I just didn't look through it carefully enough. I didn't see it show you how to find the number of electrons for ions if you're counting. So I'm going to show you it right now. So nitrogen, 5. Oxygen has 6, but there are 3 of them. Now, if you see a negative, that means that it has gained an electron. And so if it's a -1, we have to add an electron. If it was a -2, you'd add 2 electrons. If it was a -3 charge, you'd add 3 electrons, because that's technically what it means, right? When you have a negative charge on something, it gained an electron. And so there are 24 electrons. But if you were to draw the Lewis dot structure, you could draw any one of these structures, and they would be considered equivalent to one another. So some people might draw the double bond at the bottom. Some people might draw the double bond on the left. Some people might draw the double bond on the right. Doesn't matter. They're all equivalent because literally all you've done is you've moved these, electrons and basically rotated your molecule 120 degrees. That's all you basically have done. So that's what a resonance structure is. It's the same structure in reality. It's just, they're all equivalent to one another. There's more than one valid Lewis dot structure. And so in reality, if we're looking at the bonds themselves, or if we're looking at the bond energy itself, the actual structure, so the nitrate ion, is an average of all three of these possible resonance structures. So just keep that in mind. If it wasn't an average, then this bond would be a lot shorter, and these bonds would be a lot longer. But in reality, because the electrons are free to move around, it actually is. I was going to say equidistant. That's probably not a good word to use. But it is basically as if you averaged all three of these to measure what the bond length would be for an oxygen, which is kind of cool, I think. And again, I tried to describe this before it even came up, but I should have waited until this little bullet point came up. Electrons are really delocalized. They can move around the entire molecule. So even though we like to show them as being these, solid lines, these electrons here are just as free to move all the way over here to this oxygen or that oxygen. They're not bonded in place, and stuck in one location. The electrons can actually move anywhere they want within this entire molecule. So let's draw a Lewis dot structure for each of the following. So two of them are going to have resonance structures and one of them doesn't, but I kind of wanted to at least start with something that looks kind of cool. So carbon monoxide, CO. So if we add them up, we need to have 10 electrons. And so here is what we would have. This is how I would start, actually. 2, 4, 6, 8, 10, right? So I have 10 electrons. This doesn't have an octet, though. So I would start by making a double bond. Still doesn't have an octet here, though, this carbon. So I would do a triple bond. I'd be left with this. So this is generally regarded as, the correct Lewis dot structure for carbon monoxide. But you're not following the octet rule here, which is why I would say that these are still incorrect. But technically, these are resonance structures. Which one is the one that exists? This. But they're resonance structures. There are different ways of representing something. So here we have methanol. So methanol, I have 4 from the carbon, 3 from these hydrogens, 6 from this oxygen, and then 1 from this hydrogen. So I've got 14. It looks something like this, which is kind of cool. You've got, your single hydrogen bonds here. You've got your carbon-oxygen bond here. You've got your oxygen-hydrogen bond here, and you've got your lone pairs of electrons on the oxygen here, which looks kind of cool, I think. And technically, yes, there are resonance or would be resonance structures for it, but this would be the correct way of drawing your methanol. This one is really cool. You've got OCN minus. Forget what that one is called. It's not cyanate. Maybe it is cyanate. But you've got OCN minus. So I've got 6 from the oxygen, 4 from the carbon, 5 from the nitrogen. And notice it's a negative sign here. So that's +1. That's 16 electrons. And so these are all valid structures. I could have a single bond nitrogen carbon here, and then a triple bond for my carbon oxygen. I could move that so that I have a triple bond for the nitrogen and carbon, where I have only a single bond between the carbon and the oxygen. I could do a double bond here and a double bond here. These are all considered equivalent to one another. Which one's the most correct? Well, I can't even point out that to you yet because we haven't talked about 8.13. Now let's talk about how we could figure out which one is the most correct Lewis dot structure, though. Great. So we have all these different ways of drawing Lewis dot structures now, and some have multiple resonance structures. So how are we supposed to figure out which one's correct? So the way that it works is like this. Atoms in molecules will try to achieve formal charges, which, by the way, if you're wondering what is a formal charge, it is a housekeeping or bookkeeping method of figuring out which is the correct Lewis dot structure. Does it have any bearing on reality? Not really, but formal charges are useful in figuring out whether or not a Lewis dot structure is more correct than another one is. Okay, so generally speaking, formal charges want to be as close to zero as possible. Any negative formal charges, so if you have a negative charge that you could end up getting, then you would expect them to reside on the most electronegative atoms. So that's why we put electrons, generally speaking, when we're doing Lewis dot structures, on the more electronegative atom first, before we move on to putting dots onto the other atoms. And that's also generally why the central atom tends to be the one that has that is the more positive, whereas the outer atoms tend to be more electronegative. And again, I said tend to. There are exceptions. So formal charges, though, how do we calculate that? So there's no exception to figuring out formal charge, though. It's the number of valence electrons that are on the free neutral atom minus the number of valence electrons assigned to the atom in the molecule itself. So what do we assume? Again, remember, models all have assumptions. So for this, what are we assuming? The lone pairs of electrons belong entirely to the atom in question. Yes, that isn't true. What did we just say? The electrons can move anywhere, but we're pretending like those lone pairs of electrons are stuck and belong entirely to just the atom in question. Shared electrons, that would mean ones that are in bonds, are divided equally between the two shared atoms. So how do we calculate them? Sum up all of the lone pairs of electrons, subtract the number of assigned electrons from the number of valence electrons on the free neutral atom. Well, let's do an example. So we have POCl3. Let's assign formal charges to each atom. So I want to figure out what's the formal charge on my phosphorus, what's my formal charge on a chlorine, what is my formal charge on an oxygen. So I have three different types of atoms in this, and I want to know what the formal charge is. So again, number of valence electrons minus the number of valence electrons assigned to the atom in the molecule. Okay, first things first, phosphorus. So phosphorus should have 5 electrons around itself in its free and neutral state. That's just directly from the periodic table, right? Now, how many bonds does it have? 4. So 5 minus 4 is +1. That means the formal charge of this phosphorus is a +1. Oxygen. Oxygen has 6 in its free and neutral form. Okay, so that means, again, from the periodic table, it has 6. How many bonds does it have, though, here with its lone pairs included? I have 6 plus 1 electron from this bond. That means this oxygen has a -1 charge. What about the chlorine? All right, chlorine wants to have 7. It has 1, 2, 3, 4, 5, 6, plus 1 from here, 7. So these would be the formal charges: a +1, a -1, 0, 0, 0. All right. Now, what are our rules? A little rule governing for our formal charges here. So the sum of the formal charges of atoms in a given molecule or ion must equal the overall charge on that species. So in other words, if we were looking at something like sulfate has a -2 charge, all of your formal charges would have to add up to a -2. POCl3 was neutral, so notice that we had 0, 0, 0, +1, -1, that's overall 0. Okay. So here's a good one. How can we figure out whether this would be a more correct way of drawing CO2's Lewis dot structure or this one? So spoiler alert, we already said that this was a Lewis dot structure for carbon dioxide. Some people, inevitably, when they're trying to draw the Lewis dot structure for carbon dioxide, draw this instead. Or maybe the triple bond on this side and a single bond on that side, but still, you get the idea. Why is this one not the one we go with? Why do we always draw CO2 like this? Well, let's find the formal charges. Now, this one, there are actually 2 oxygens here, and each of them have different bonds. So we actually have to separate them. So let's talk about this first one. Oxygen in its neutral state has 6, and I have 7. Oxygen in its neutral state has 6. Now, how many do I have in my bonds here? So I have 1, 2, 3, 4, 5. So 6 minus 5 is a +1. This oxygen would have a +1 formal charge. Carbon starts with 4. We have 4 bonds. That's 0. What about this oxygen? So this oxygen, again, starts with 6. Minus 7, though, because I have 1, 2, 3, 4, 5, 6, plus 1 from this bond. That's minus 1. So this has a plus 1. This has a 0. This has a minus 1. Let's try this one. So these oxygens are actually equivalent to each other because they both have the exact same bonding structures. This has a double bond with 4 lone pairs. This has a double bond with 4 lone pairs. So they're the exact same thing. So that's 6 minus 1, 2, 3, 4, 5, 6, 0. Carbon, 4 minus 4, because again, we have one single electron coming from these ones, 0. So the reason why we say that carbon dioxide has this Lewis dot structure, and the reason why we use it isn't because this is impossible, okay? It's just more unlikely. And it's more unlikely because these are resonance structures of each other, but this has a separated charge where, remember, oxygen is more electronegative than carbon. It would never want to have a plus 1 anyway, but we're kind of forcing it to have a plus 1, and this one has a minus 1. So this has charges that are, separated from each other. This one doesn't. This one has the lowest possible formal charges where everything has a formal charge of 0. Last but not least, the valence shell electron pair repulsion theory model. So the structure around a given atom is determined by minimizing the electron repulsions that we have. So you can picture them like magnets. Okay, when we're drawing our Lewis dot structures, it's a flat structure. It's not three-dimensional, but those little dots that we've been drawing are all lone pairs of electrons. Those lone pairs of electrons are going to interfere with each other. And more importantly, if we're looking at atoms, they're going to interfere with the atoms and push atoms out of the way. So what we want to look at is minimizing the repulsions of our electron pairs on our molecules. And so thankfully, there is a chart we can use in order to do so, but it will determine the positions of the atoms and how they're being shared. So the Lewis dot structure part of this is really just great. You have a two-dimensional structure. Then what we're going to do is we're going to look at a chart in order to figure out what the general shape would be of that molecule. Now, do you have to know the shapes? Yeah, you have to know the shapes. Do you have to memorize the shapes? Yeah, you have to memorize the shapes and the bond angles of them also. And that will determine the position of all of the atoms in your molecule, okay? So here's the chart. If you only have, if you have a central atom along with 2 atoms on the outside and there are no lone pairs of electrons on your central atom, it is a linear geometry. On the other hand, if you have, a central atom with 3 things, trigonal planar. If you have a central atom with 2 atoms and a lone pair of electrons, it's bent. Then we have 4 outer atoms, that's tetrahedral, 3 outer atoms and a lone pair of electrons on the center, trigonal pyramidal. Bent again if we have 2 and 2. We have 5, we get a trigonal bipyramidal. If we have 4 in a lone pair, that's called a seesaw or a sawhorse. I always say seesaw. You have T-shaped, you have linear, you have, this one got cut off, this is octahedral, this one is square pyramidal, this one is square planar, this one is T-shaped, this one is linear. Okay, and so, and this doesn't have bond angles, but I'll trust me, your book has a gigantic chart like this, and the bond angles are included in that. Now, the nice thing is that, especially for things like this, so this is already getting really long. This video is going on for way, way, way too long. So what I'm going to do is just kind of tell you the answers to these, but I will show you a simulation that's free that can help you model these things. So we have HCN, pH3, SF4. So HCN is linear, 180-degree angle. pH3, trigonal pyramid, 109.5 degrees, right? Technically, it's less than 109.5 degrees. It's about 107. Technically, I think in the book, it just says less than 109.5 degrees. And then SF4 is a seesaw, or what did it say on that chart? Sawhorse? I've actually never seen that one before. I always say seesaw. It has 90-degree angles and 120 and the 120-degree difference also. O3, that's ozone, is bent with 120 degrees. Technically, it's a little less, I think, than 120 degrees. we've got KRF4, that's square planar with a 90-degree angle and 180-degree angle, again, depending on what we're looking at conceptually. So this is a PhET simulation. It's free, okay? And it allows you to add bonds to things in order to see bond angles, which is kind of cool, and then also to tell you what the geometry is. So you can see the bond angle and the shape, and you can just add another bond. We get trigonal planar, then tetrahedral, then trigonal bipyramidal, and then we get octahedral. And again, you can move them around. Now, again, this model that you're seeing here is a model. So it's not perfect. This is not for real molecules, but it's, again, a really good approximation of that. So notice that I can add a pair, on a lone pair of electrons, and now it's bent. Technically, this would be less than 120 now, though. Same thing with this. I can add another one. Then we have, maybe like a cool T shape. Again, I just like playing around with this. So you can kind of add or subtract lone pairs. Here's what a seesaw actually would look like, which is kind of cool. Let's add another one. Now we got square planar. So it's a free simulation. I'll put it in the description so you can play around with it. But it's a great way of utilizing and trying to use VSEPR theory to predict what the shape of different geometries would be. But true or false? So it says a molecule that has polar bonds will always be polar. If true, explain why. If false, provide a counterexample. So the answer is false. Remember, a polar bond just means that we have, a difference in electronegativity. And that doesn't necessarily mean that it's going to be a polar substance. How do we know that? Well, we literally just looked at CO2. So there is a difference in electronegativity between oxygen and carbon, but it's a symmetrical molecule, so the dipoles end up canceling out. What about this? Lone pairs make a molecule polar. False, again, right? Lone pairs of electrons don't necessarily equal polarity. It's possible to have something like this, xenon tetrafluoride, where we now have two lone pairs of electrons, which, again, so you can barely see it here, and it did get cut off again. It's square planar, and square planar means that this dipole is getting pulled equally in all four directions at a 90-degree angle here. And so it ends up canceling out and being nonpolar. So simply because you see lone pairs doesn't instantly mean that we have something that's going to be polar. All right. And so that's where we're going to have to end for the day, because I am tired and I'm sure you are too. This was huge. This was a gigantic section. So feel free to like and subscribe. If you have any questions, leave a comment, and then I will do my best to move on to chapter 9 next. All right. So thank you very much.